Hey, this is the second video about orbits, and this one is going to deal with Kepler's laws. And Kepler's laws are really, really cool, partly because they're empirical. Kepler came up with them based entirely on observations. He did not know anything about gravity, really. They're just purely descriptive of the way planets move. And historically, they're about 100 years before Newton. When Newton said he was standing on the shoulders of giants, mostly he meant Kepler. Because without Kepler's data, Newton could not have come up with the law of gravity. So Kepler's first law says that planets move in elliptical orbits with the sun at one focus. Now this is important because prior to Kepler, everyone assumed that planets moved in circles. There was disagreement on whether they were moving in circles around the Earth or around the sun, but everyone before Kepler agreed that they moved in circles, which meant, among other things, that Copernicus's otherwise correct theory about the planets orbiting the sun still wasn't very accurate. But with the idea that the orbits are elliptical rather than circular, that did make the theory fit the observations. And so an ellipse is kind of a flattened circle, but the way it's defined is that it has two foci, and those foci, if we look at the distance from the first focus, R1, and the distance from the second focus, R2, that those distances, R1 plus R2, is equal to a constant, defines all the points on the ellipse. Now some other things to define. The longest distance across the ellipse is called the major axis, and the semi-major axis A is half of that distance. Generally, the larger a planet's semi-major axis is, the longer its orbital period will take. And then there's also eccentricity, which is complicated, but it's essentially a measure of how non-circular the ellipse is. A circle has eccentricity of 0. The more not like a circle the ellipse looks, the greater the eccentricity. You definitely need to know the semi-major axis. You need to have a qualitative understanding of eccentricity, but you don't need to know its mathematical definition. If you're interested, your book has that. And now the other important thing is the sun is not at the center of the ellipse. The sun is at one of the foci. The result is that planets are sometimes farther away from the sun than they are at other times. Now the Earth and all the other planets have relatively low eccentricity orbits. Pluto's the only one where the eccentricity, I believe, exceeds 0.1. But certain things, comets for instance, have highly eccentric orbits, so they come in really close to the sun sometimes and then go really far away. That's Kepler's first law. Kepler's second law says that equal areas are swept out in equal times. If I draw an elliptical, that's kind of a crappy ellipse, let's try again. Still kind of crappy, but a little bit better. So let's say we draw the ellipse, we put the sun at one focus of it, and we look at some time when the planet is close to the sun. And the planet takes a certain amount of time, delta t, to move from one point to the next. And if we draw two lines connecting those 2 points to the sun, and then define the area swept out as A1, so the area contained in that, that's A1. Now at some other point here, let's say now we have the planet, it goes between two other points. It's the same elapsed time, delta t, and we define the area in the same way. Call that A2. And so the idea is that if the same amount of time is represented in each of those two movements, then A1 equals A2 if the two delta t's are equal. And that is a very complicated geometrical way of expressing something that we can understand more simply because we now have more physics knowledge than Kepler did, which is Let's say equal areas are swept out in equal times. That means if you look at the rate at which area is swept out, that will be a constant. And so the rate at which area is swept out is a derivative, dA dt, equals a constant. But if you look at the area of this little sector here, so we've got a small sector of the orbit, here's the sun, there's the area, we treat that as a sector of a circle. Now this angle I'll call theta, and the distance I'll call r. R isn't changing rapidly during this small time t. And so the area of that sector equals r squared theta over 2. If theta were 2 pi, it would be a complete circle, and the area would be pi r squared. So we have d dt of r squared times theta over 2 is a constant. Now r isn't changing very fast. It's essentially a constant for our purposes. And so this becomes r squared over 2 times d theta dt is a constant. And d theta dt, that's the rate of change of the angle, that is the angular speed. And so we have r squared omega divided by 2 is equal to a constant. And since 2 is also a constant, and the mass of the planet is also a constant, we can say that mr squared omega is a constant. But if you recall back from our last unit, rotation, mr squared omega is the angular momentum. So angular momentum is a constant, and that means angular momentum is conserved during an orbit. That's very important. So Kepler's second law is one way of stating conservation of angular momentum. Very, very, very important. The angular momentum of a planet is conserved. That means we can do things like calculate its speed at various points given its speed at other points. It also means that we can determine that the force exerted on the planet by the sun points toward the sun because the torque has to be 0. So the torque is always equal to 0. That means the force points toward the pivot point. Which is interesting. It also means that the planet is going faster when it's close to the sun and slower when it's far from the sun. And now we get to Kepler's third law, which is one we saw last year. The cube of the radius is proportional to the square of the period. So we're going to derive it for a circular orbit, but it also happens to be valid for elliptical orbits as well. So cube of the radius. So what we'll do is we'll start by assuming a circular orbit, sun mass m, planet mass little m, orbit of radius r, moving at speed v. Now the speed v, we'll say, is equal to the distance traveled during one orbit, 2 pi r, divided by the time of one orbit, which is t. So that's the first step. The next step is to say that the net force on the planet is the gravitational force. That's the only one that's important. And that happens to be equal to the mass of the planet times its acceleration. And so we get gm over r squared, but since it's going in a circle, the acceleration is v squared over r. And then what we do is we substitute this expression for v into this equation. We get gm over r equals 4 pi squared r squared over t squared. Simplification gives us r cubed equals gm over 4 pi squared times t squared, which does in fact show that the period of the orbit, or the square of the period, is proportional to the cube of the radius. Now keep in mind that Newton's derivation actually went the other way. He started with Kepler's third law, and from that figured out the inverse square law, which is a whole lot more impressive than what I just did. But this is the important thing. Don't memorize that equation. You should, however, know how to derive it. That shows up on the AP exam every few years. Also, another thing to notice, the period of a planet does not depend on the planet's mass. It only depends on the mass of the sun. So the larger the sun is, the shorter the period will be for a given radius. And now let's look at an example, which is problem 44 from your textbook. Let's say we want to put a satellite in a circular orbit about Earth with a radius equal to half the radius of the moon's orbit. Question is, what is the period of the revolution? So there's the Earth. Here's our satellite. Call that r over 2. Here's the moon's orbit with radius r. Now the moon has a period of 27.3 days. You can look that up in the back of your textbook, one of the appendices. And so we want to find the period of the satellite. Now we use Kepler's third law, and we don't need to know the mass of the Earth or the gravitational constant to use it. Because what we say is that if we look at r cubed over t squared, that just equals gmm, or no, not gmm, it equals gm over 4 pi squared, which is a constant. And so we can say that this quantity for the moon equals the quantity for the satellite, rs and ts. A bit of algebra gives us the period of the satellite equals the period of the moon times the radius of the satellite divided by the radius of the moon to the 3/2 power. Plugging in numbers gives us the period of the satellite is 9.7 days, which is pretty large. Most satellites have a period of no more than 24 hours, and most of them have a period of only a few hours, which tells us most satellites are not nearly that high above the Earth. Now for tomorrow, you'll need to look at question 12. That's what I'll be checking.